From the studios at WMFE in Orlando, Florida, this is the Space Exploration Podcast asking the question, are we there yet? We're stepping away from Mars this week and even outside our solar system for some big news in the scientific community. This month, NASA's Kepler telescope discovered more than 1,000 new planets outside our solar system. They're called exoplanets, and the total count is now at about 3,000 confirmed planets. But the hunt is on for what we call Goldilocks planets. These are planets that aren't too hot, not too cold, and just right for pooling water. You get it? Like the Three Bears, Goldilocks. Anyways, Kepler is leading the charge, finding and confirming these planets, and along with ground-based systems, we think we've discovered about 36 Goldilocks planets. Pretty cool, right? Well, Kepler is just one step in this search for exoplanets, Goldilocks planets, and a step closer in answering the question, are we alone? Kepler's only looking at a tiny fraction of the sky. The Transiting Exoplanet Survey Satellite, or TESS for short, is the next chapter in the search for other worlds. Stephen Reinhardt is project scientist on the Transiting Exoplanet Survey Satellite, or TESS, and he joins me from NASA's Goddard Space Flight Center. Stephen, thanks for joining me.
Oh, thank you for having me.
So, first of all, let's start with the basics here. What's an exoplanet?
So, an exoplanet is simply speaking, a planet around a star that's not our own. We have obviously known about planets in our own solar system for thousands of years, but only in the past 20 years or so have we really started to know that there are planets around lots of stars and be able to detect them directly, or indirectly, as the case may be.
And so, why are we looking for them? What kind of value do they add to the scientific or community?
Well, so there's a number of reasons that exoplanets are interesting. One of the biggest ones is sort of the deeper philosophical question of, are we alone? Is the Earth a unique object? Are there lots of Earth-like planets out there? And eventually, we'd really like to understand, is life common? Is life ubiquitous in the universe? Or is humanity and life on Earth really an unusual occurrence? And the first step to looking for those signs of life is in finding the planets themselves. It's also interesting from what I refer to as comparative planetology. You know, we have these 8 planets in our solar system. I still don't count Pluto. And they're all different from one another, right? They're all really kind of unique. And that's really amazing and cool. And, you know, from a planetary science perspective, that's really, really interesting. But now we're seeing thousands of these new exoplanets. And what we've learned in our limited ability to actually study the individual objects is that there's even more diversity in planets out there. There's as many different kinds of unique planets as there are planets at some level. So one of the things we're really trying to understand is just, you know, what makes different planets the way they are. So by looking at all these different exoplanets, we can start to talk about how perhaps our own planets formed, how our solar system formed, and how the solar system will evolve over time.
So you're looking for exoplanets that are around other stars. That's pretty far away. How do folks like you actually find these exoplanets?
So for TESS, actually, we're looking at stars that we consider nearby, within about 200 light years or so. The way we look for this is we look for a transit event. So in fact, on May 9, the Mercury will be transiting the sun. So with the right equipment, don't do it with your naked eye, you could go outside and you could actually watch the transit of Mercury. We're looking for the same thing. If a planet is orbiting a star, let's say 150 light years away, and if that orbit is aligned to our line of sight correctly, then once per year of that planet, once per orbital period, then the planet will pass in front of the star relative to our line of sight. So we don't see the shadow of the planet like we would for a Mercury transit, but what we see is that some small fraction of the light from that star gets blocked by the planet. And so the star appears to get dimmer just a little bit. So for instance, Jupiter around the sun would lead to about a 1% drop in the brightness of the sunlight, the light from the sun. Earth would be about 1/100th of 1% drop in the brightness. So we look for those tiny little dips in the brightness that are caused by transiting exoplanets.
Interesting. So it's kind of like if you're in a living room and somebody walks in front of a lamp. It kind of dims and then it gets bright again.
Right, that's exactly right, except that, you know, I'm much bigger than a light bulb, so I block all of the light, whereas these planets are blocking just a very, very small fraction.
So it's my understanding that the Kepler spacecraft has been kind of performing this same kind of observation What has it found? It's been in orbit since 2009, if I'm correct. What has it
That's
found?
correct. So far, Kepler has detected over, I think it's around 1,000 exoplanets now, confirmed exoplanets, and there are thousands more exoplanet candidates. Um, the whole purpose of Kepler was to basically conduct a census. It was how many planets are out there, what different kinds of planets are out there, how common are planets around different kinds of stars and different kinds of planets. So uh, really the goal was to figure out how common Earth-sized planets were. It was really a statistical mission, but it used the same transit method. It just looked at one particular patch of the sky for a long, long time, and so it looked much, much deeper as well. So whereas TESS is focused on only the nearest 200 light years or so, Kepler looked at about 3,000 light years. But it was really there to do a count, to just do that census and count up how many planets there are.
1,000 exoplanets, is that what you expected to find with Kepler, or did that kind of smash your expectations?
So before Kepler, we really didn't know. There were some guesses about how many planets would be out there, but we didn't know if just how common or how rare they were. There had been a few detections of transits from ground-based surveys, and there had been a number of detections using the radial velocity method from the ground, but the uncertainty in the statistics was so large that we really didn't know for a fact. We knew that they weren't so rare that we were going to see none. We knew we'd see at least some exoplanets, but we didn't know that they are as common as they are. Now, because of Kepler, we know that they are, in fact, really quite common. There are as many planets in our galaxy as there are stars, which is a heck of a lot of planets.
Now, before Kepler, you said there was some ground-based ways to kind of see these exoplanets. Can you kind of explain what we were doing before we had these space observatories?
Well, so the most successful method that was used from the ground, and people are still doing this from the ground, is the radial velocity method. And conceptually, this is actually pretty easy to think about. It's the reflex motion of the star. So when you have a planet orbiting a star, really the star isn't fixed in position. Both the planet and the star orbit the center of mass, right? If you imagine, if I take my 4-year-old and we swing around and I hold her at the arm's length and swing her around, then I have to lean backwards so that I don't fall over. We're actually both doing this little circle around our center of mass. So as the planet makes one orbit and goes in a big circle, the star does a tiny little pirouette. And when it does that, you can look at the spectral lines from the star, and as it moves towards us, we get a little bit of a blue shift in the spectral lines from the star. As it moves away from us, we get a little bit of a red shift. So we can use the Doppler effect and that reflex motion together to get an assessment of how much the star is moving. That tells you that there is a planet, and it tells you how massive that planet is.
What's the constraints on that method? Can you only see so far out with that, or is it not as detailed as a space observatory?
Well, so there are a couple of constraints. One is that it has the same issue as the transit does, that you have to have a good alignment of the system. If the planet is orbiting perpendicular to your line of sight, right? So imagine it tracing a circle in the sky as you're looking at it, then you don't see any reflex motion, right? Because the star is now moving around, but it's moving around horizontally instead of towards and away from you.
Right.
Now, if you have both a transit and an RV, then you can constrain what that orbit is very, very well. But generally, you don't have that. Even when you do see that radial velocity motion, when you see those Doppler shifts, you don't necessarily know exactly what the inclination angle is. So if you imagine that you've got a very, very big Jupiter-sized planet in a close orbit around a star, but it's inclined at a 45 degree angle relative to our line of sight, then the star is in fact moving away and towards us and away from us as the planet orbits it, but not as much as if there were no inclination, if that planet were exactly aligned with our line of sight. So there's an ambiguity that's the M sin I. Basically, without knowing the inclination angle, there's always an ambiguity in the mass of the planet that you've measured. There's a second constraint, which is that the method that we use is high-resolution spectroscopy. So these are very, very delicate, precise fantastic instruments that people have built to do this. And they do spectroscopy that's very, very fine. So they break up the light into many, 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 many channels. That means that you actually need relatively bright stars to be able to do it quickly. So if you try looking at things that are far away, it takes an extremely long period of time. So this is why, for instance, for Kepler, we talk about of order 1,000 planets that have been confirmed. Only about 300 of those have been confirmed with radial velocity measurements. Most of the other thousands of candidates, we can't confirm those because, or we can, but it will take a really long time because they're far enough away that doing this RV measurement is really hard. They're just too faint.
Gotcha. Well, let's talk a little bit about the TESS spacecraft. Kind of give me a sense of what the equipment is on it and where it's going to sit and what it's going to do.
So TESS has 4 cameras. Each one of those cameras has a 24 by 24 degree field of view, so that's a pretty big chunk of the sky. Together, those 4 cameras look at adjacent fields. So it's a strip 24 by 96 degrees of the sky, and it will go all the way from about 6 degrees above the ecliptic plane to just about 6 degrees above the ecliptic pole. So it's you can imagine, if you imagine a globe, just take a rectangle and paste it down with the center of the top quadrant, top detector being pinned down to the North Pole. And then every 27 days, move that whole block around that pivot point, around the pole, and do that 13 times until you've covered the entire hemisphere. So these 4 cameras will be used to observe about 200,000 stars in the course of a 2-year mission. The first year will be really only the northern hemisphere or the southern. We have to decide which one we start with. And then the second year we'll flip around and do the other hemisphere. And so after 2 years, we'll have observed about 200,000 stars. We'll also have obtained full frame images where we take a picture of the entire 24 by 96 degree field of view. And those data are going to be really great for not only exoplanets, but for a lot of other astrophysics.
In comparison to Kepler, how many stars did Kepler look at?
So Kepler, I got to remember, I think Kepler looked at a few 100,000 as well. I can't remember the exact number off the top of my head.
Okay, I was just trying to compare to how many. Now, is TESS looking at those same stars? Or
So the important thing is that, whereas I mentioned before that Kepler looks out about 3,000 light years, TESS does the whole sky, but it only looks at those stars within about 200 light years. And this comes back to the limitation that we just talked about of the RV surveys, of those radial velocity method, that whereas a relatively small fraction of the Kepler targets are bright enough that they're really good for radial velocity follow-up, for TESS, they all will be, because they're all bright stars. On average, the TESS stars are between 30 and 100 times brighter than Kepler stars. So for Kepler, when they discover a new batch of exoplanets, the next question they ask is, which ones of these can we do good follow-up on? Which ones can we try to confirm with the radial velocity measurement? For TESS, instead of asking which one, it's which one do we do first? Because all of them will be good candidates. It's just a question of, it'll be a prioritization as a rather than an ability question.
So if I'm getting this straight, TESS isn't going up there to confirm Kepler exoplanets. You're basically looking at exoplanets that are confirmable by that radio velocity technology you have on the ground, right?
That's right. So Kepler was really about statistics. TESS is about, I guess, to put it succinctly, it's about generating a target list for the future. The thousands of exoplanets that TESS will find will all be around bright stars. They will be great targets for both ground-based follow-up and follow-up with space missions. We can get the radial velocity measurements to measure the masses of all of those planets. And of course, I get from the transit measurement itself, I get the radius of the planet, because the bigger the planet, the more light it blocks from the star. From the radial velocity measurement, I get the mass. Put those two things together, and I have the bulk density, the average density of the planet. So now I can tell you, is that made out of rock? Is it water? Is it something weird like a chunk of iron? Maybe it's a gas planet. You can start to talk about the gross characteristics of what that planet is like. On top of that, for some of the planets around these bright stars, you'll be able to do what we call transit spectroscopy. And the really cool thing about that is that if you imagine for a moment that you have a small planet with a big atmosphere, and that atmosphere only absorbs light at one particular wavelength, then if you were to, and it's transparent at all other wavelengths, if you were to watch the transit of that planet at some wavelength where it doesn't absorb, then all you'll see is the rock. The atmosphere is transmitting completely, so the planet looks like it's a certain size. But in that wavelength where the atmosphere absorbs, the planet suddenly appears to be bigger because the atmosphere is blocking all the light there too. So when we take these transit spectroscopy measurements, what we effectively get is the planet size as a function of wavelength. And that we can use to start to understand what's in the atmosphere, what the actual atmospheres of these planets are made out of. Now we can talk about, is there oxygen on a planet? Is there methane? Are there signs of habitability? Is there something weird about? We can really start to compare planets to one another on more than just their density.
So you can pretty much find out quite a bit of stuff from these observations you're making.
Well, right. So TESS is the starting point. We won't make those transit spectroscopy measurements ourselves. TESS doesn't do that. TESS is going to find the objects, is going to make a list of objects that people will use the James Webb Space Telescope, and they'll be using ground-based facilities and Hubble and everything they can get their hands on to try to get those kinds of transit spectroscopy measurements so that we can start to actually understand the planets. So TESS is opening a door to this field of what I call comparative planetology. It doesn't do it itself, but without it, we couldn't do it.
Now, how is the development of TESS going? Is that spacecraft completed and just waiting for a ride to orbit, or are you still kind of working on putting it together?
Well, so in the NASA jargon, we're in Phase D. Phase D is the implementation phase, so we're building everything now. Everything is underway. The instrument itself is being built at the MIT Kavli Institute and at Lincoln Labs, and they're getting the pieces put together and they're testing the components for the instrument, and we aim to launch sometime next year.
How big is it? Give me a sense of size.
So it's shorter than me, and I'm not that tall. It's about, imagine, I've got several good analogies, but they're not good analogies for everybody. They're about 5 foot tall and maybe, less than a meter around. I mean, think of a really large barrel.
Okay.
It's not a huge spacecraft.
Gotcha. How does this play into the larger scale of deep space exploration? I mean, you touched upon it and how these are going to be, targets for other observatories, but are you hoping that's something that you discover with TESS and further investigate, that you'll actually send a probe like a New Horizon or Deep Space probe to go check out these exoplanets?
Well, I would love that. That may be a long way in the future. I think that so if we're successful, I think that we are likely to find several habitable zone planets, Earth-sized planets in the habitable zones of their host stars. So places that might be hospitable for life as we know it. I would love to see us send something to one of them. But of course, these are going to be light years away, and if we're lucky, they're within about 10 light years. So that's a long round trip, or even a long one-way trip, to send anything out there to take a closer look. I think I would love to do it, but that may be a long ways away. We've got a lot of stuff in our own solar system to explore still too.
Gotcha. And just for clarification, TESS is going to be sitting in an Earth orbit taking observations, right?
Yeah, it's actually a really cool orbit. It's a 2-to-1 Earth-Moon resonant orbit. So it's this gigantic ellipse that goes out almost to the orbit of the moon, and it does 2 orbits for every 1 orbit of the moon. And so what that does is it comes close to Earth, and then it goes far, far out for 13.7 days, and then it comes back close to Earth again. And we get when we come to close to Earth, we can dump all the data down because we've got a lot of data. But during that long cruise, you get lots of time to look at your targets without having to without getting interrupted by the Earth getting in your way. So it's really actually it's a pretty neat orbit if you're into that sort of geeky thing.
That is pretty cool. Are there any other spacecraft that are doing that now?
There are other spacecraft who have used that kind of orbit as part of getting to where they want to go, but I think this is the first one that's actually living in that kind of orbit.
That's pretty cool. And so you said that this is the mission scheduled for about 2 years. How many photographs, how many observations are you hoping to take in that 2-year period? And is there the possibility for it to extend past that 2 years?
So I can't completely answer that first question. I can give you an idea, though. So,
okay, yeah.
There are 200,000 stars in the core science data. For each of those things, we'll take a postage stamp image, but a 10 by 10 pixel picture around that one star. Those pictures will be taken every 2 minutes while the object is in the field of view. So you can sort of do the math. I can't do it in my head right now, but every 2 minutes for 200,000 targets for 27 days each.
A lot.
It's a lot. And then on top of that, there are those full frame images I mentioned before, where we acquire a picture of the entire 24 by 96 degree field of view, and those we get every 30 minutes. So it's a lot of pictures. It's a lot of data. Every 30 minutes. That's 48 images a day for 365 days a year for 2 years. That's a lot of data. The nominal mission is 2 years. That's how long it takes us to actually survey almost the entire sky. We do hope that if everything is working well, that we will continue observing into a third year, maybe even a fourth. Of course, that's that will be reviewed by the agency and by the community to decide whether it's a priority for us to do or not. If we go into that longer mission, then we'll have to think about how to optimize our search for what we want to do. Do we want to try to optimize it for finding more habitable zone planets? Do we want to optimize it for searching the ecliptic plane for other kinds of objects? What do we really want to do? And that's a debate that we'll be having until such time as we start asking to be extended. As soon as we ask, we'll have to actually have an answer for what we're going to do with the extended time, but not yet.
With missions like this, like TESS, like James Webb coming up, we're getting a much clearer view of space and observing it. Is there anything in particular in the next few years that you're especially excited about or really want to focus on? Like, is there one exoplanet or one little segment of the sky that you really want to see?
Oh boy. Well, there's a ton of things that I think are really interesting. Of course, recent gravitational wave discoveries have been fascinating. Some of the exoplanet discoveries have just been amazing. I've really been excited to be working on TESS because of some of the things that we've found with exoplanets. And one of the great things with exoplanets is that we never stop being surprised. I think there's always something new that we don't expect, and it just doesn't seem to ever stop. I think my biggest hope for TESS is that we find more things that I can't predict. If I could predict it right now, then I expect to find it. And finding things you expect to find is not so much fun as being surprised by something new and exciting. So I'm hoping that whatever it is, it will be something that I just couldn't imagine right now. Now, the part of the sky that I'm most interested in really is the North Ecliptic Pole, because I mentioned that there's these. The field of view of TESS is one of those cameras is centered on the North Ecliptic Pole. Well, that means that for every observing sector, we still look at that region. So there's this 12-degree circle on the sky where we'll observe all the targets in there for a full year. That also happens to be the same part of the sky that the James Webb Telescope can look at any time of the year. So any object you find there, you could immediately follow up with JWST, and that means that those targets are going to be really great for extensive scrutiny once we know that they're there. So I just hope that they're different. I hope that we'll find something that nobody expected.
Stephen Reinhardt is project scientist on the Transiting Exoplanet Survey Satellite, or TESS, and he's speaking with me from NASA's Goddard Space Flight Center. Stephen, thank you so much.
Thank you.
Well, that about does it for this episode. Support for Are We There Yet comes from the listeners of WMFE. You can follow the show online. We're on Twitter at AWTYMars, Are We There Yet Mars, or reach out to me in the Twitterverse. I'm at Space Brendan. Be sure to leave us a review if you listen to us on iTunes. That's how new people learn about this podcast. Are We There Yet is a production of WMFE. Our theme music was composed by Kevin McLeod. Find more space news online at WMFE.org/space. I'm Brendan Byrne. Thanks for listening.